Alright, ladies and gentlemen, this is going to be our next video on the cell membrane. So let's get started on this next video. So how does the cell membrane help us maintain homeostasis? Let's make sure we review homeostasis first to understand what it actually means. So homeostasis is the ability to maintain a constant internal environment in response to environmental changes. Now, how does this cell membrane allow us to maintain homeostasis within cells and then within our bodies? Well, cell membranes help organisms maintain homeostasis by controlling which substances may enter or leave the cells. Remember, we need to have the cells intact, so therefore we need to control what goes in and out of them to make sure they're functioning properly so that they can function in our body. So if we were to zoom in on the cell membrane, we might see something like this. And in the cell membrane, it's going to have a variety of different things. We have glycoproteins. There are glycolipids. We obviously have the phospholipid bilayer, which we've been talking about this entire time. We're going to have cholesterol molecules in between. There are going to be channel proteins and integral proteins in this membrane. Now, we call the model here the fluid mosaic model. So when we're looking at this particular diagram here, or this model, we reference it in science as the fluid mosaic model. So what I want to do first is review the phospholipid bilayer, since this is what makes up a majority of the cell membrane. So let's go through and look at the phospholipid bilayer again in a little more detail. So remember, phospholipids are going to make up the cell membrane. That's what the vast majority of the cell membrane is going to be. They have hydrophilic heads and hydrophobic tails. Now remember, this is important because it's going to go through and allow for certain molecules to pass through dependent upon their size, and then it's going to prevent other molecules from going through to maintain homeostasis and to regulate what goes in and out of this cell. So a phospholipid, remember, it consists of a couple of different parts. It's a lipid containing a phosphate group in its molecule. And remember, it has a partial charge based on the polarity. We have a phosphate and choline head. We're then going to have our fatty acid tails attached to our glycerol here. And because of this, what we get are partial charges amongst the molecule. And we have a hydrophilic head and that hydrophobic tail. This is really important for us to understand transport through the cell membrane. And let's go through and look at a channel protein and understand the function of channel proteins in the cell membrane. Now, a channel protein is going to be really, really important. A channel protein is a protein that allows the transport of specific substances across the cells. So some molecules are not going to be big enough for us to go through and pass through the phospholipid bilayer, or the polarity is not going to allow for it. So let's say this molecule is much too large to pass through. Can't go through the phospholipid bilayer, but what the cell can do is have a channel that fits the specific shape and polarity of that molecule, allowing it to pass through. A channel protein is simply a gate that allows those molecules to move from one side of the phospholipid bilayer to another. So let's go through and look at glycolipids. So glycolipids are really, really important, and we're going to see them attached to the phospholipids on the tops of the layer. And they're represented by this green. And glycolipids are lipids with a carbohydrate attached by a glycidic covalent bond. We don't have to understand that, but remember, it's just attached to the lipid via a bond. And the role is to maintain stability of the cell membrane. So it's going to kind of keep the cell membrane together, but it's also going to facilitate cellular recognition. Now, let's say we have some white blood cells floating around in our body. They're going to go up to these glycolipids, and they're going to sense, based on the shape and the polarity of these lipids, whether or not this is an invading cell, a cell that's not native to our body, or a cell that is native to our body. And it's going to know, okay, this cell is made, it's part of our body, so those white blood cells will not go through and destroy that cell because that's a cell that was produced by our body. Again, this is helping maintain homeostasis because it's allowing for cellular recognition. So let's go through and look at glycoproteins. Now, glycoproteins are going to be somewhat similar. Now, these are molecules that consist of a carbohydrate plus a protein. Now, this is going to be really, really important for cell recognition and facilitate cell signaling. So just what we talked about with the white blood cells, they're going to enable for cell recognition and ensure that our white blood cells know that these are cells within our body. They're not invading cells. But they're also going to allow for cell-to-cell recognition and the transport of molecules so that way cells can go through and communicate with each other. Now let's go through and look at cholesterol and understand it. Now cholesterol is also going to be very important for maintaining the fluidity in the cell. Now, these cholesterol molecules can go through and allow for fluidity changes based on temperature. So if it gets really, really cold, well, the cholesterol molecules are going to ensure that the cell membrane doesn't freeze and become solid and very rigid and not allow it to go through and regulate what goes in and out of the cell. Now, in the same token, what the cholesterol is also going to do is ensure that the fluidity of the cell membrane remains stable when the temperatures also get very high. Temperatures get too high, we don't want the cell membrane to fall apart, so the cholesterol molecules are going to ensure that it stays together. Now, it's important to understand we don't have to have a protein channel for all molecules. Let's say we had these carbon dioxide and oxygen molecules. They are actually going to be small enough to go in between the phospholipids, and the polarity is going to be consistent enough with the phospholipid bilayer to allow them to just go through and diffuse through the membrane. So if the molecules are small enough and the polarity is appropriate, the molecules will just diffuse through the membrane. And we see this with oxygen and carbon dioxide. So if we kind of think about this, well, we have the cell membrane, and the cell membrane is also known as the fluid mosaic model. And that's what we see right here. Now, a vast majority of the fluid mosaic model, or the cell membrane, well, it's made out of phospholipids. And phospholipids are amphipathic. So amphipathic, which means that they have a hydrophilic head and hydrophobic tails. And then they are also small and unchanged. Now, if we go here, there are also proteins within the fluid mosaic model. And these proteins allow for transport. And these are generally large and charged. So when we're talking about phospholipids, they are generally small, and the charges amongst the hydrophilic and hydrophobic tails, when we're talking about small and uncharged, we're saying it's a neutral overall charge within that molecule. And generally, we're going to see large and charged proteins that allow for transportation within the cell membrane.